All right. So these are my notes on Module 1, section on descriptive statistics and visualizing information. We're going to go over some examples of efficacy and applications. DSVI is especially effective in communicating information and supporting reasoning about data. Okay, as the data sets grow larger and larger, it becomes essential to use summaries. And common types of statistical summaries include numerical methods and graphical methods. And let's start by going over some graphical summaries of data. And of course, we might agree that deciphering images is a bit more easy than numbers, than sorting out numbers. Of course, the type of data and the visualization goal determine the visualization method. Okay, so let's talk about data visualization. Obviously, we have pie charts and dot plots that are ideal for qualitative data. Okay, so when we're trying to plot categories, okay, such as colors or product types, geographic places, lexical categories, and so on. Okay, and so we see that regular number lines and bar graphs are standard and conventional for quantitative data. For example, positive integers or the letters of the alphabet. And this is because ordering and distance between numbers convey important information. All right, so let's go ahead and start by plotting, just like in Module 1, a pie chart and dot plot set. All right, so let's say, for instance, that we were studying fermionic statistics of leptons, or something to that effect. And we wanted to compare in some experiment sets of leptons by atomic mass. Okay, so let's assume this as a context in which we might want to illustrate and diagram numerical information about some class of elementary particles, in this case leptons. All right, so no big deal. All right, so let's start out by setting up the individual sections of the pie chart, and I'll remain faithful to the numerical values given in the example of Module 1. And what we'll see in a moment here is that the actual rendering of the chart is, in fact, order-preserving relative to the code block for the chart. So we have a section that corresponds to 45% of the sample size. We have a section that corresponds to 13% of the sample size. We have a section that corresponds to 15%, one that corresponds to 18%, and one that corresponds to 20% of the sample size. Okay, so let's say that 45% of the total is formed by a collection of electron mass. Let's say that merely 13% of the total is formed by a collection of electron-neutrino mass. Let's say that 15% of the total is formed by a collection of muon mass. Suppose that 18% of the total is formed by a collection of muon-neutrino mass. And finally, we have 20% of the total formed by a collection of tau electrons. All right, so let's just go ahead and position and stylize the labels themselves. Great. Next, let's set up the list plot or dot plot for the same data set. Okay, let's start by listing the respective data points. The important thing to observe here, in terms of Mathematica syntax, is that the x value of each ordered pair represents the percentage incidence, or spread, per lepton mass category, and the y values simply aid in separating the data points horizontally so that we can more easily compare their relative positions visually. Next, we just need to label the tick marks of the respective axes as follows. Starting with the x-axis, we're going to separate each of the tick marks on the x-axis by a distance of, let's say, 10 points. All right, and then next, let's go ahead and label the y-axis with the respective elementary particle name. And again, we're going to separate each tick mark by a distance of 10 points. Cool. All right, let's see what this all looks like. Okay, perfect. And then lastly, let's just label this list or set of graphs. Perfect. Right, so each point in the list plot, or dot plot, corresponds to a percentage where the intervals on the x-axis are percentiles. Comparing two categories, which we'll call proportionality gauging, is easier in a dot plot. So this was mentioned in section 1 of module 1. So it's easier to judge or compare to each other the relative positions of respective quantities on a horizontal line. Kind of like in a relay race or a track and field race, where you're sort of getting a side profile, or in this case a bird's eye view profile of essentially which section is ahead, right? So it's easier to look at it visually that way. Alternatively, a pie chart makes it easier to see what percentage of a total a category represents. And let's also just mention that on a dot plot, we would first have to refer to the x-axis to figure out any portion of the total. Okay, and once again, let's mention that with bar graphs and number lines, order and distance between data points convey critical information. Okay, so let's review this simple problem in a slightly different context. Suppose we're asked to show how many units of a particular good were sold in various international markets. What are the most suitable visualization techniques that we could use in that context? Well, it wouldn't be a pie chart. Dot plots are good. And bar graphs would be good because, again, we're dealing with quantity. So in general, rule of thumb, when we're dealing with quantitative comparisons, or relative comparisons, I suppose, you want to think instinctively bar graph or dot plot. And certainly one of the critical takeaways is that the bar graph or chart is essentially a dot plot turned on its side. Okay, let's work out a quick example of a bar graph. And suppose we wanted to collect the number of trades executed by 18 associates of, let's say, a proprietary trading firm or something. Okay, Mathematica allows us to do that in just a couple of lines of code. Very good. All right, so let's work out another example of a bar graph. And in this case, we're going to chart out the number of successful airplane landings by airplane model on consecutive days in January of 2024. And we're going to group each day by ordered triplets of models. Model 1 has 1 successful landing on January 1st. Model 2 has 2 successful landings on January 1st, and Model 3 has 3 successful landings on January 1st. For January 2nd, Model 1 has 1 successful landing, Model 2 has 3 successful landings, and Model 3 has 3 successful landings. For January 3rd, Model 1 has 5 successful landings, Model 2 has 2 successful landings, and Model 3 has 1 successful landing. The airplane models are ordered on the x-axis, and the number of landings are handled as y-coordinates. We'll designate a unique color for each airplane model. Next, we're going to label the consecutive days of January 24 and indicators for the respective models, Model 1, Model 2, Model 3. And then lastly, let's just label the chart. So again, number of successful landings by airplane model on consecutive days in January 24. All right, let's see what this looks like. Cool. Okay, so let's quickly go over the section on histograms. The histogram is a type of bar graph, but it allows for blocks with different widths. I'd say one of the principal ideas to understand is that the areas of the blocks are proportional to frequency, and the total area, or sample, corresponds to 100%. Now this definition that I've written down here is, I think, so we're asked to come up with our own definition during Section 1, Module 1. And so here's mine. A histogram is a diagram consisting of rectangles whose areas are proportional to the frequency of a variable and whose widths are equal to the sizes of each respective class into which a range of a variable is divided. I'm thinking about a definition of frequency in the context of hertz, for example. Okay, so frequency is the number of occurrences of a repeating event per unit of time. Very straightforward. All right, so let's look at some code. Okay, so the syntax for this code stack rectangle chart is quite similar to the bar graph above. We're going to start by spelling out the respective fields. And these are slightly different from those given in Section 1, Module 1. So let's bear that in mind. Let's label our axes and stylize the individual bars to our liking. And then lastly, we just need to label the tick marks along the x-axis. All right, great. Right, so what's going on here? So, as pointed out by Professor Walter, the percentage of a sample falling into a block range can be figured out without vertical scale, since the total area equals 100%. Nevertheless, vertical scale, i.e. density scale, which is given in percent per unit, retains arithmetic precision. And this is due to the fact that the area of a block corresponds to a percentage. Area is computed by the formula A equals width times height. And since width is given in unit U, in this case years, the unit for the height must be given in percent per year for uniformity. So the histogram gives two types of information about the data. First, the notion of density, or synonymously crowding or clustering. So in this case, the height of the bar tells us how many subjects there are for 1 unit on the horizontal scale. For example, the highest density is around age 39, as 0.059 or 5.9% of all subjects are 39. In contrast, only about 0.005 or 0.5% of subjects fall into each 1-year range for ages 70 to 80. And the second type of information, which can be gleaned from the histogram, is the notion of relative frequency. Okay, so percentages as relative frequency. Let's look at some more code. And so the trouble with the web implementation of Mathematica Notebook is that we simply don't have comprehensive LaTeX typesetting available to us. So there is a way to sort of code up block equations and do vertical and horizontal alignment for marking up block equations, but it's just not as expressive mathematically. So I'm going to just show how to do it quickly in our computable document here. So in Mathematica, we do have this function grid box available to us, and it can be quite useful in terms of matrix computations and things like that, but as far as just typesetting mathematics, it's not going to be our standard solution. I just want to show that you could use it if you wanted to. So here's what that would look like. We have this function grid box, which allows us to align expressions and gives us a bit of control over the column alignments and the column spacing and the display form. So it's not too bad, it's just not what we're used to in terms of LaTeX typesetting or tech typesetting, or tech typesetting if you want to be linguistically precise. Okay, so let's go ahead and compare that to a different solution that we might come up with. So once more, we're just trying to sort out, arithmetically, what percentage of people fall into a certain age range in a given histogram, where the metrics are time and percent per unit of time. Let's do the calculation in LaTeX. So we just need to set up an HTML file, pull in the MathJax CDN, screenshot the markup rendering, and pull that PNG file into our Mathematica document. So we have width, given in years, times height, given in percent per year, equals, and then we can parenthesize for the rules of arithmetic, width times height, percent, and the unit of year cancels out. And so we end up with width times height, percent, as the answer to the question, what percentage of people fall into a certain age range in a given histogram, such as the one described above. And we see that the units do in fact work out arithmetically. All right, so let's just go ahead and grab that screenshot. And we can rename it for convenience and drop it right into the Mathematica document. And for good measure, let's go ahead and add the LaTeX script to the document as a plain text cell. That way we have everything in one place. Voila. So that's the formula. Now let's go ahead and work out the previous example in LaTeX. So compute the percentage of people falling into the age range 70 to 80. All right, so the range of time on the x-axis being considered is 10 years. There are approximately 0.5% per each year in that range. Therefore, per the rules of arithmetic, there are approximately 5% of the total sample size falling into the range 70 to 80. So let's repeat our procedure of grabbing that screenshot and pulling it into the document. Perfect. All right, and we will spell it out. Approximately 5% of all subjects fall into the age range 70 to 80. Great. So if you have any questions, shoot me a message, leave a comment. Remember to hit the like button, subscribe to the channel, and I'll see you in the next one.